Okay, in this video, we're going to continue or take a look at the problem that we worked on in class, which is the 3 blocks connected by 2 different strings. So the first thing that you want to notice here is that you do have 2 different strings, right? Or ropes or cables. This one that's connected through the pulley, and remember the purpose of the pulley is to change direction of tension. So this one is going to have a tension in that direction, this one a tension in that direction, but they are both the result of what I'm going to call rope 2. Then you have this rope connecting these 2 together here, which we're going to call rope 1. So we have 3 masses, 2 different ropes, and the earth involved in our system. So if we go to our whiteboard and we want to think about our system of interaction here. Oops. So in our system, we have the 1 kilogram block, we have a 2 kilogram block, and we have a 4 kilogram block. The earth, rope 1, and rope 2. As we see, the earth, of course, is going to act on each one of those, giving us the force of gravity. Rope 1 acts on 1 kilogram and the 2 kilogram. And then rope 2 acts on the 4 kilogram. So if we look at this as a system, we would have these 3, right? Different masses. And if we take a look at each one of the masses, we might draw a force diagram or a free body diagram for the 1 kilogram mass to look like this. We'd have the force of gravity of the 1. So make sure you're clearly subscripting to say that you're talking about the 1 kilogram mass. And then we have the tension 1 pulling up on it. So we know it is accelerating. So if we go back to that diagram, we know that the acceleration is going to be pulling that upwards, right? So looking at this, we assume that we have acceleration acting down on this side and acceleration acting up on this side. So it does say that it accelerates. It's going to be our first question to calculate that acceleration. As long as they stay together, those accelerations are going to be the same magnitude, but we need to recognize their directions. So because of that, T1 must be greater than FG1 if it's going to be accelerating upwards. For mass of the 2 kilogram, you're going to have the force of gravity of 2. You're going to have tension T1, and these 2 are of the same value because they are ropes, right? Not because of necessarily action or reaction, but because they are both of the same rope that is tight. And then you're going to have lifting that one up, T2. For the third mass, which is a mass of 4 kilograms, right? You're going to have the force of gravity pulling it down. And I'm going to label that force G4. And if I again imagine this boundary system, right? It only has then T2 pulling it back up. And these 2 are equal. So T2s and T1 is what we have here. So what we notice right away is we can solve, right? If we list what we know, what we want to know. But some things that I'm going to do right away is to recognize, well, I could look at this system, depending on what I'm looking at and what I'm trying to find, as this as being 1 mass, right? If I do that, then I don't necessarily look at that T1 as another rope. So this would have a total mass of 3 kilograms. So that's another possibility of how we can take a look at this problem. So that's me combining rope 1 along with the 1 and the 2, which makes it so that we only have an interaction of, whoops, and I left out one of our interaction lines. Rope 2 goes to number 2. So from outside of this boundary surface going around all of that, we only have the earth and rope 2. So we have mass 4. Another concept is to then say, put that down, we'll go into our orange. Try to keep everything color-coded. For mass of a 3 kilogram, then we would only have FG3 and our tension 2. Okay, so that's an option depending on how we want to solve the problem. So what I'm going to list, what I know, is that I know that this has a mass of 1 kilogram. So the force of gravity of 1 is going to be the mass 1 times g. So that's going to be 1 kilogram times 9.8 meters per second. So FG1 is equal to 9.81 newtons. The mass 2 is equal to 2 kilograms. So F, force of gravity on mass 2, is mass 2 times g. So that's going to be our 2 kilograms times 9.81 meters per second squared. So remember, this is giving us our magnitude of the weight, 19.62 newtons. We know that this one, mass 4, is equal to 4 kilograms. The force of gravity of mass 4 is equal to mass 4 times g. That's equal to 4 kilograms times 9.81 meters per second squared. This is a force, so we get units of kilogram meter per second squared, which is a newton. So we get 39.24 newtons. For this one, we have mass 3, which is the combine of the 1 and the 2. So that's going to be 3 kilograms. Force of gravity of number 3 is equal to mass 3 times g. That is equal to 3 kilograms times 9.81 meters per second squared. So FG3 is equal to the 3 times the 9.81 for 29.43 newtons. So that's how we begin the problem. That's what we know, right? That's our system diagram, our free body diagrams, and what we know. We also know that all of their accelerations, acceleration of 1 magnitude is equal to the acceleration of 2, right, is equal to the acceleration of 3, which is going to be equal to the acceleration of 4, which we're just going to let that equal a. And this is because the string is tight, right? So the string or the rope, just to be consistent in my words, the rope is tight. All masses move together. So what are we looking for? If we go back to our problem, we are looking for part A. What is the acceleration of the 4 kilogram block? So we're really looking for the acceleration of any of it. So if I go back to my diagrams and my values here, okay, if I want the acceleration of the 4, my beginning equation might say, I'm going to do this underneath number 4, the summation of forces in the y direction of number 4 is equal to mass 4, acceleration of 4. So if I go to my picture, the summation of forces is going to be T2 as a vector added to vector force of gravity of 4, right, equals mass 4, acceleration of 4. So I do know my mass and I do know my gravity, right? But I have 2 unknowns here, T2 and A4. So I need to do a little reasoning here to say, well, that gives me one equation with 2 unknowns. If I can find another equation that contains the same variables, then I might be able to solve for this using simultaneous equations. So what we get here is the magnitude of T2 minus the magnitude of the gravitational pull on the 4 kilogram is equal to mass 4 times the magnitude of the acceleration, which we just called A, right? But it is a vector, so we need to recognize that this one is going to be going down, right? So just as we made this a negative, the negative force of gravity, we need to recognize that that is going down. So we do want to make this a negative value. We're not going to subtract it, but it should have a negative value to it because it is going down. So we get T2 minus FG4 equals negative M4 times A. Because we called A up here was what we're representing all of our accelerations with. So I need to find another equation that contains these same letters. And then look at mass number 3. We take a look at that. So if we take a look at mass number 3, we will see that mass number 3 will contain these same variables. So I'm going to write that equation under mass 3 here. We're going to have the summation of forces in the y. Sorry. For mass 3 equals mass 3 A3. So we will have T2 plus force of gravity 3 equals mass 3 acceleration 3. So the magnitude of T2 minus FG3 equals mass 3 times the magnitude of 3 acceleration. We recognize that this is going to be going up, so that's going to be positive. So we get T2 equal to mass 3 times the magnitude of the acceleration of 3 plus FG3. Over here, we got T2 to equal negative M4A plus FG4. So if these two are equal to each other, then the right sides are also equal to each other. So if I set the right sides, which only has the A in it, then I should be able to solve for the A. So that's what we're going to do. We're going to say that negative, just to do that in a different color, negative mass 4 times A plus the force of gravity of 4 is equal to mass 3 times the same acceleration plus the force of gravity of 3. So subtracting the m3a from this side, subtracting the fg4 on that side, we get negative mass 4a minus mass 3a equals fg3 minus fg4. So now I just have the a on the left side. So this is going to be 4 kilograms negative times a minus 3 kilograms times a equals 29.43 newtons minus 39.24 newtons. So on this side, you get negative 7 kilograms times a equals negative 9.81 newtons. So to get the a by itself, we'll divide by negative 7 kilograms divided by negative 7 kilograms. We get our acceleration equal to a positive 1.4 meters per second squared. So that is the magnitude of the acceleration of number 4 and all of the blocks. So remember, we said up here that acceleration is equal. So that means all the blocks are moving with that same acceleration of 1.4. So if I go back to part B, what is the tension in the string supporting the 4 kilogram box? If I go over here, I'm really talking about T2. So what I'm asking for in part B is what is tension 2. So going back to our pictures or equations, where does tension 2 show up? In boxes, or looking at masses 4 and the 3 or 4 and the 2. So I'm just simply going to go back to this equation here and substitute in our acceleration, right? So if I go here, then for part B, I just need to solve for T2, which is equal to negative 4 times a plus the force of gravity of 4. So T2 is equal to negative 4 times 1.4, and this would be in units of kilograms, plus the force of gravity of 4, 39.24. Going to be 5.6 newtons negative plus 39.24. So 39.24 minus the 5.6 tension 2 equal to 33.64 newtons. That's going to be the magnitude of T2. So notice in here, I apologize, but at this point we recognize we have dropped our vector notation, right? And that's simply because in the previous line, right here, we're looking at the magnitudes of all of those vector quantities. We've already taken consideration their direction through the negatives, so we can just write them as regular variables because we kept everything positive and negative. Okay, finally, taking a look at part C, what's the tension in the string connected to the 1 kilogram box? So now I go back to here, and again, I take a look at my pictures. What we're really looking for there is what is T1. T1 is showing up in mass 1 and mass 2. Mass 1 is easier, just has those two forces. I'm going to choose to use mass 1 to solve for part C. So for part C, we'll see is what is T1. Okay, so we're going to take a look again at so using the 1 kilogram mass, we will see that the summation of forces, in the y equals mass 1 acceleration of mass. You will have T1 pulling up on it plus the force of gravity of mass 1 equals mass 1 times the magnitude of the acceleration of mass 1. So you get, oops, guess I'm stepping ahead there. Mass 1, A1, and now we're going to get rid of our vector notation. So we get T1 minus the force of gravity of number 1 equals mass 1 acceleration 1. So T1, again, dropping the vector notation, is going to be M1 A1 plus the force of gravity of 1. That's 1 kilogram. They all accelerate the same, so I use the same magnitude of acceleration of 1.4 meters per second squared plus the force of gravity of 1, which is 9.81 newtons, equal to 1.4 newtons plus 9.81 newtons. T1 comes out to be 11.21 newtons. Which, go back and we make sense of this, right? So what we're doing is, well, go back to this picture. I'm pulling up on T1 with 11.1 newtons, and it's pulling back down due to gravity, right? But since the upward force is more than the 9.81 weight, it begins to lift it. We should see the same thing here. This one begins to lift number 2, but at the same time, number 1 is pulling it back, right? But the tension in number 2 is also greater than the weight of all 3 of these, and therefore it begins to rise. Whereas over here, the tension is less than the weight, and therefore it begins to fall. So, trying to have that so you can all look at it in one spot. That's the solution to the mass problem. So you can clearly see the importance of keeping things in order. So remember, we draw our picture, we list what we know, what we want to know, rewrite our equations to figure that all out. So that's with all of this, writing the equations. We recognize that we have 2 variables and 2 equations with 2 unknown variables. So solving for one variable, setting them equal to each other, you can then get down to just one variable. And then once you get the answer to that one variable, use it to plug in to get the second variable. So from here on down, for the most part, it's just your algebra, right? This part is the most important, the beginning. So please continue to practice that.